Hi, my name is Divansh Modi. My project is emotion recognition from speech. And emotion recognition from speech works as follows. So we have an input speech. We extract the audio features. So these are the audio features: ZCR, zero crossing rate, chroma shift, MFCC, RMSC, spectrogram, roll-off, centroid, contrast, bandwidth, tonnage. We also augment the data with additional noise, stretching, shifting, and pitching of the audio. Then we pass these features to emotion recognition model, and it predicts one emotion out of the given six emotions. So now we'll be going through the installation and the usage process for the project. Okay. So for the installation, the first important things is to download the libraries. So these are the important libraries that need to be downloaded. The next thing is downloading the data sets. So this is the link to download the data set for RavDes. Similarly for Crema, the test and survey. So these are the data set links. Additionally, one can mail me to download the data sets. So this is how the data sets are organized on my Google Drive. So these all data sets belong inside this folder, that is audio file. So as you can see, this is a test audio wave, that is Surrey, Crema, and Savvy data sets. So you can request me and I can gain access to my Google Drive, or you can download the data sets from the links shown. So as mentioned, it's necessary to download the libraries. So as this is the installation and usage video, I'll show you the both the process side by side. Okay, so first we need to download the libraries, and then just shift enter to import all the required libraries. For the installation and the usage, keep the code sequence as mentioned in the Google Colab file. Now this is the decorator function. We can use this decorator function simply above any function by using @ symbol at the beginning, that is @calc_time. And the use of this decorator function is to give the total required time for the function to execute. Okay. So as I told, this is the installation usage video, and we'll be covering in combiningly both the processes. So first we imported the required libraries. Then we saw a decorator function. Now we have to do the pre-processing on the data sets. Okay. So this is the path where the data set for RavDes is stored. So once you download the data set, provide the path of the RavDes data set. The rest, all the pre-processing function and everything doesn't need to be changed. It will be taken care of. Just provide the part details. Perfect. Similarly for Crema, provide the part details for the Crema data set. Installation process mainly is about copying my code and making sure the path are correct for every dataset, CSV files, model files. So the installation process in short involves changing paths and giving proper paths. Similarly for test dataset, Savvy dataset. Okay, and now we have this fetch data function. Fetch data function, what it will do is it will call RavDes, Crema, test, Savvy dataset function, and it will combine the output of all those data sets and store in a CSV file. Okay, so we need to give a path to store the CSV file again. Again, shift enter and run this code cell. Okay. Yeah. So Now, and you can see I've used the decorator over here, that is calc underscore time. So it will give me the total time required for fetch data function to execute. Then we have this data augmentation functions, that is noise augmentation, stretch, shift augmentation, pitch augmentation, extract features. So this function, what it will do is, given the data and the sampling rate, it will extract the features. So it's extra from the audio. So it extracts a zero crossing rate, chroma shift, melt frequency, substrate coefficients, root mean square energy, melt spectrogram, roll off, spectral centroids, contrast, bandwidth, Carnets, and it stacks in, it stacks all those features and returns them. And you can see this get features function, in which I'm reading the data from the path. Then I'm calling these extract feature function. Then adding some augmentation to my existing audio. That's it. So run this, shift run this cell. The audio features extract. Again, provide the necessary path wherever it is required. So this function is a one-time run function. So run the cells only if you are doing a setup initially, that is, you are extracting the features. This is used basically to extract features, and it is a one-time process. Okay, so you don't need to run this cell again and again once the features have been extracted. And this function takes the highest amount of time compared to all other functions in the code, because it extracts the features. You can see the total time required also. So as you can see, I've already extracted the features, so I'm not running this audio features extract function again. Okay, so this is the plot graph function, which is used to plot loss and accuracy curves. Then we have the additional preprocess function. This was used to carry out the exploratory data analysis on the data, because once I downloaded the data, extracted the features, the labels and emotions, I find out that there is not uniformity in the label names or the emotion names. So I need to create the uniformity. So I replace the word sadness with sad, happiness with happy. So I have a uniformity in the emotions. Then I dropped out the surprise and calm labels because they didn't have sufficient amount of samples, and that could lead to a misclassification. Okay. So again, this audio feature final function, provide the path change. Here we are doing the one hot encoding of the labels. Then we apply our min-max scaling to the features. Then we split the data into 80, 10, 10. That is 80% train, 10% validation and testing. Shift enter and run this cell. In this cell also we have our emotion recognition model. Here we have reduce on plateau, which is used to monitor the loss. And if the plateau is encountered, that is the loss is flat, then it reduces the learning rate. We have an early stopping condition, so it has a patience of 20, so it waits for the 20 epochs, and if still the loss after till the 20th epochs remains the same, then holds the training at the 21st epoch. We have a checkpoint file path, so give a path to store our model file. There is the checkpoint file, and this checkpoint file gets stored at every epoch or checkpoint, which gives the highest validation accuracy for that particular checkpoint or epoch. Okay, so we have a residual net kind of architecture, that is ResNet kind of architecture for training a model. And so we have these dense layers, we have the residual blocks with different filters and number of convolutions. At the end, we have a fully connected architecture of two dense layers. There is a 256 dense 256 activation ReLU and dense 128 activation ReLU. So this creates a one fully connected architecture of dense layers, and then we have the final dense layer, which contains the class information. Activation function is softmax. Okay. We are compiling a model using the categorical cross entropy loss. As emotions labels that we have are nothing but the categorical categories or categories. We have categorical cross entropy loss. Optimizer we are using is Adam with initial learning rate set to 1 e minus 4 and decay after 50 epochs. So that is after 50 epochs it will reduce the learning rate. After every 50 epochs it will reduce the learning rate. Then we have this audio HTML file which tells the collab that collab to invoke the microphone and record the audio of the user input. Okay. And then so for that we have, so this is a JavaScript part which tells the collab to invoke the microphone of the user. Then we have this get audio function which first calls the audio underscore HTML, that is the JavaScript part. Then it opens the invokes the microphone of the user, and then we can record a voice. That's it. So again, shift enter, run this function. So this get underscore features underscore recorded, it is for extracting the features recorded by the user in real time, that is a real time user input. Okay. Then we have the test real time function. So test real time function, again that we have a path change. So load the model file from the path. We are providing this path to store the .npy files and CSV file. So again, there's a path change over here. Provide the appropriate path. Okay. So you can see we record the audio of the user, then we extract the features and apply the scaling, then we pass those features to our model for prediction, and then model returns the predicted output. Okay. So this function is all about that, and this function will be used extensively when we are testing on the user input speech. Okay. This is the evaluate model function. And again, we are loading a model to provide a path change over here. This function is used to evaluate the training, testing, and validation accuracy once the model is trained, and it displays the classification report and the confusion matrix output. Okay, so this function, the main function. So if you don't want to set up the whole thing, the beginning from the training, and if you just want to use my testing part, so you can use the test real-time function shown above. Otherwise, if you want to set up it from the ground zero, copy the code, run all the part, and run this main function. So the main function, what it does is it is used to build the model that we saw above, that is the emotion recognition model. It builds the model and it saves the model at every epoch or checkpoint. The best parameters of model which give the highest validation accuracy get saved, okay, at every epoch or checkpoint. So this main function is a one-time run function, and all the hyperparameters and everything is set. Just need to call this main function. So this main function will get the data, train the model, and save the model at every epoch or checkpoint which gives the highest validation accuracy, and it will also evaluate the model after the model is trained. So as we discussed earlier, that we need to maintain the uniformity in the labels or the emotions. So we renamed a few labels and emotions, and you can see the count of the labels or emotions, and based on the count we decided to drop the surprise and count because that's sufficiently less number of samples compared to the others, and these less samples can cause a big problem in misclassification when training the deep learning neural network model. Okay, this is the size of the train test validation set. He says this guy is told that I have a very complex ResNet kind of neural network model. As you can see, these are the different layers of my model. Okay, so this is a whole. This whole is a model, and you can see the number of trainable parameters for my model. These are the number of trainable parameters. So this is how the model starts training. So you can see epoch 1, epoch 2. Okay, so as you can see, the validation accuracy gets improved. So the checkpoint file is updated. Checkpoint, so that you can see the validation accuracy gets improved from this minus n to 0.50824. So for this checkpoint or this epoch, the emotion recognition file with the best parameters is saved. Yeah, as you can see, these are the for the different epochs. As the validation accuracy gets improved, so again you can see that the validation accuracy improved from this 0.57 to 0.58. So for this particular epoch, the emotion recognition model file gets updated and gets saved with those best parameters. Okay, so those best parameters, and as you can see, I'd use the early stopping condition. So after 180 epochs, there is no further decrease in the loss function, loss output, right? So it stops the training, and the best validation accuracy that I get is 76.76, or you can say 76%. This is the total number of or total amount of time required for training the model. Okay. So this is the output of the evaluate function, that is the training accuracy, testing accuracy, and validation accuracy. You can see 76.12. This is a classification report. The 0, 1, 2, 3, 4 is nothing but the different emotions or labels, and I'll show you what they mean in the below output. So this is a confusion matrix, and you can see the loss and the accuracy curves, and you can see that after 150th epoch, the training accuracy is almost similar or same, that is or near equivalent 99%, and the loss still keeps on reducing after 175th epoch. Also the loss is still getting reduced, so it's a good sign that the model has trained perfectly and it's not overfitted or underfitted. Now just we want to test our model. So, and again I told that this main function is a one-time function, so we just run it once and then it's done. Now we want to test the model in real time, so we call this function first to test the model in real time. Now as I told that I'll show you the meaning of the 0, 1, 2, 3, 4 in the classification report. So this is the meaning of the 0, 1, 2, 3, 4s in the classification report. These are the different emotions, and these are the different one-hot encoding embeddings for that. Okay. So we can see that this one-hot encoding maps to the emotion sad. Similarly, this maps to the emotion neutral. Okay. So the 0 means the emotion is angry. 1 means the emotion is disgust. 2 means the emotion is fear. 3 means the emotion is happy. 4 means the emotion is neutral, and 5 means the emotion is sad. Okay. So 0, 1, 2, 3, 4, 5, and its mapping can be seen in the output of these two. Okay, so now we want to just test our function in real time. So what? So I have to run this function, test real time. Okay, it takes input the encoder. So encoder. So this is the encoder returned by this function output. So we are just using this encoder in this. Okay. So now you have to just test this function. What this will do is it will first invoke and ask for the permission to record audio. So then we'll record the audio. Then we have to click on stop button to stop recording, and then it will give out. Hey, hi, how are you? Yeah. So as you can see, it recorded my recorded my audio. It displayed a graph of my audio, and you can see it has predicted the emotion as happy. right? Also, you can listen your audio and you can make a prediction from your audio as well. Okay, so as you can see, my audio displays my mood, that is happy, and similarly, my model also predicted happy. Again, you can listen the audio. So this is how the emotion recognition from speech works. Now, this is a bit extra work that I had done for my research. It's not required for your, if you want to set up at your side, it's not required to do. But I did this for my research work because I wanted to know how universal compatible is my model for different languages in different dialects and in different audios. Okay, so it depends that every audio may have a maybe in different languages, maybe have different dialect, maybe have different harmonics in that. So I did it for testing on unknown audio samples. So I took few unknown audio samples from the different data sets. Like I Google and find out the different data sets and collected audio samples from those. Like some of the audio samples are labeled, some are not. Okay, and I'm using this different audio samples to check the universal compatibility of my model. So if you want to do the same, what you can do is you can just provide the path of the different audio samples over here. The rest all process remains the same. No changes, only the change in path. Okay, and this function, this is diff lang test function, is used to test my model on the unknown audio samples, or you can say the unknown audio samples in different languages, different dialects, and harmonics. That's it. So this whole covers the installation, setup, and usage of my project. Also, make sure that when you are testing my model, test in a background reluctant environment, because the background noise may affect the output of the emotions, because currently there is no audio segmentation being used. If audio segmentation is used, we can segment the speaker voice from background noise and can just feed the speaker voice. So this is a future work of audio segmentation, combining the other two models, that is the textual based and facial based model for emotion recognition. And I'm actively looking to develop these models in future. Currently, my emotion recognition model provides the best accuracy compared to the authors, and it can be seen in the README file and the research report of mine. So this is the basic working of the emotion recognition model. And if you want to set up the whole model, run the functions in a sequence as mentioned in the collab file. If you just want to test my model, you can download the emotion recognition.hd5 model file, and you can just use the test real-time function to test in real time. Also make sure the functions used inside the functions are executed before, to avoid any errors. So maintain the sequence of execution of the functions similar to the one that is there in my collab file.